I'll just jump in real quick, and yeah, I don't mind any in-depth discussions or want to get this over with quickly. So definitely feel free to interrupt if you have questions. So yeah, basically tried to make some visualization of what I took away from last week's research meeting about representing time. It's kind of a mix of in the brain and in Monty. Hopefully it works. And yeah, maybe you can just let me know if you took away the same broad concepts or other things. So as a first example, I took a melody. So let me just explain this figure. Can you see my cursor? Okay. So this is what's being experienced. There's time, and I'm going to move this kind of gray bar towards the right, and it kind of goes through that melody. And then up here, this is the kind of shot clock or stopwatch kind of mechanism that we talked about. And I think I'll refer to it as a stopwatch mechanism now because I visualize it kind of like a stopwatch where basically you start it, this arrow moves through it, and then you can reset the stopwatch, kind of lap to lap or reset, and and this arrow goes back to the top and starts moving around again. And you can reset it again, it goes back up and moves again. Reset it, it goes back up, and so on. And basically, whichever point the arrow is currently pointing at is the input to layer one. And that basically represents the timing since the last event. And what I mentioned is this clock gets reset with every significant event that was sensed. So for example, in the example of the melody, I'm basically saying each of those notes is a significant event. So whenever it hears any note, doesn't matter which note it is, but any note it hears, it resets this clock. And then as soon as it resets, it starts moving again clockwise around. And wherever it points at is a kind of neural or context representation that goes into layer one. And then
And
the specific...
Oh, sorry.
Yeah,
go ahead. Say, is it a circular representation of time, or would it? Cause that I guess implies that if enough time passes, it goes back to zero. But I'm assuming it's more kind of like it just trails off, and you get slower and slower time cells.
Yeah, so I've kind of in this example avoided this issue of like what happens if there's no event by the time it gets back to the top.
Right.
I think one thing we talked about last week was that as it moves forward in time, the threshold for a significant event gets lower and lower. So maybe something really minor gets detected as an event and resets the clock. Or just something that if it gets to the end, it just resets the clock. But basically it's not really circular in the sense that once it gets here, it starts over again. It's really like to get back to zero, this is a reset. If it gets back to zero, it shouldn't really get to zero from this last point here.
Right. Cool.
Okay, so let me just step through that example. So we hear the first note, and which note it is basically the feature input to layer four. And then timing since last event, in this case, is just the very first one, since this is our very first event we're sensing. And so I added this other thing down here, which is which element in the sequence we're currently in. And right now in the first element, we would associate the time since last event and the feature at that first element. We move forward, no node detected yet. We're here, this is currently the input to layer one. Move to the next node. This is shortly before the node. This is the input to layer one. And then we hear the node. Clock gets reset. We get the feature input again. And we have this kind of reset signal triggers that we move to the next element in the sequence down here. So now we're at second element in the sequence. And then we associate the timing representation that we got just before that event happened and the feature with that element in that location in the sequence. So then again, we move in time, move forward. This is the input to layer one, move forward. Now this one is the input to layer one, move forward. Oh, okay, we hear the node reset signal. Reset signal means we move one more forward in the element in the sequence. We associate the last kind of temporal input we got and the feature with that element in the sequence. Same thing happens next node. It's really kind of the same thing. In this case, we're sensing a different feature and associating that different feature with the same element in the sequence. Now, this one is the only other interesting case because it's still the same mechanism, but just we're moving a bit further down the the stopwatch, and as you see, like as time passes, the input representation to layer 1 changes. It gets like brighter. It's a bit hard to see because I wanted to make it look aesthetically pleasing, but it's not the best, I guess, to distinguish. But it changes at every step until we get to the next event, which is sensing this node triggers a reset, which means again we move one further in the sequence and then associate again the feature we get as input and the time since the last event with that element in the sequence. And that goes on. Does that kind of make sense? Is that kind of how you were thinking of it last week as well? Or
Yeah, it's a nice animation. Yeah, I think that generally fits. I think it was still an open question in my head how we associate, like what exactly is being associated, that time thing with the what you call it, with the feature. I think this is also to me kind of the most intuitive, but I don't know if this is what Jeff had in mind, just in terms of things like if we start speeding it up or slowing it down.
so it's speeding it up and slowing it down. It's basically this blue arrow. I shouldn't have made it blue because it's not really real time. It's not this arrow. It's this one can turn at different speeds on the clock, and it turns at different speeds, but it still goes through the same sequence of neural activations. So whatever was active at this point predicts that feature in the sequence.
Right.
And you can speed up or slow down this blue arrow on the clock, basically. But it doesn't change anything in the representation here. It just changes like which of these purple features are active in layer 1.
Yeah, that makes sense. So
just to make sure I'm clear on this scheme, the clock gets reset at every note touch, right?
Yeah. At every significant event. So I have another example with the stapler that maybe goes into a couple more different cases. So yeah, that might help too with understanding in a moment. But yeah, do you want to ask some questions first?
Do we send back the tempo to the thalamus to do stuff, or is this? It looks like this would figure out how to predict based on like basically infer the pace or the tempo and predict the next step when it will come.
Yeah.
But,
so basically, go ahead.
I was just gonna say, does it send something back to the thalamus so that the next prediction is like doesn't have to infer every time? Or I'm not just a little confused about the tempo.
Yeah, so basically the idea would be that this is in the matrix cells in the thalamus. It projects to layer 1, and then the column would recognize if it gets a feature input, like basically the next feature it expects in the sequence, if that appears slightly before the expected neural representation or after, that tells it whether it needs to be slowed down or sped up. And since, like, if we think of these as SDRs, it would be kind of smoothly shifting. So I think it should be possible to tell, like, whether it was before or afterwards. And then that would be a signal that gets sent back to the matrix cells, to that kind of clock, and makes it go faster or slower. And this is a global clock. So this would then change the neural input representation inputs to layer 1 of all the other columns it projects to. So it's enough for one of them to say, oh, you should be faster or slower, or you should be reset. And that kind of changes that global signal everywhere and synchronizes everyone. So like, for example, also detecting a significant event could be anywhere. Like with the stapler example, I'm saying basically like the sound of the stapling can be an event. That's like not something that's represented in the morphological model of the stapler at all, but could be detected somewhere completely else, but it resets the global clock.
Okay. Another question is the element in sequence. What kind of representations is that? Like a 1D grid cell or?
Yeah, I was thinking of this as like basically 1D space, and you move through that space. You can only move through that space in one direction, so always move forward in time. And the kind of displacement that moves you forward through that is the reset signal from the clock, like getting the first in sequence again.
So that would be the movement. It would just like a movement in the grid cell.
Yeah, it would basically be 1D movement. And I guess if we, like this is with time, but if we have actions, then you might be able to move in in two directions through a sequence. But I haven't thought through that too much yet.
It's
That's
really
just-
hard to try to do a melody backwards or something in your mind or move through it.
Yeah, so here we don't have actions, but if you have like a hint, you can imagine opening and closing it in both directions. And maybe it's like a double sequence. You need to learn both directions, or you can go through it in both directions. I'm not sure.
But yeah, in terms of things that we kind of learn as discrete sequences, if they are long and complex, it is really hard to do them backwards. Like as a sequence, opening and closing a stapler is extremely simple. It's like, it's literally just doing that. Whereas like, yeah, saying the alphabet is really hard to do backwards. Or even being like, okay, how do I cook a lasagna backwards? I don't know. It would just be really weird. Like you'd really have to almost like think forward and then do it backwards step by step.
Yeah, so yeah, it might be that this is just something you can move through in one direction. And I guess, yeah, one thing to note is that it's also discrete. So it's not like continuous 1D string. It's like discrete elements in that sequence. But then within each interval on there, you can have different temporal representations that tile that interval space. And yeah, I think maybe I'll move to the stapler example now because that shows it a bit better. So this is an object behavior with events and also continuous changes between those events. So before, like there was no feature change between events. Every feature corresponded to a discrete event. But with moving objects, there's often like a lot of continuous change. So I think this mechanism would be able to deal with that. And as I started making this animation, I realized that using different shades of purple wasn't very useful. And so I added some kind of colored rings around the first ones at least, so you can distinguish them a bit better of what's the current input to layer one. So here's a stapler, and the red, yellow circle represents the sensor patch of where it is currently sensing in the world. And here it shows where it thinks it is in the object's reference frame. So this is basically the kind of morphological model. It has learned of where the stapler exists and what features exist at those locations. This is the layer 6A locations. And so here we are at the first time step again. We get the first representation as input, and we're detecting kind of a flow pattern in this direction, this change. And so we're associating that change with this time since last event at this element in the sequence at this location. And then the stapler moves a bit. We detect this change. We have a different time since the last event. We have not detected a significant event, so no time reset yet. But since there is a different representation up here already, we can still make a new association with this slightly different flow pattern we detected. And then we move further, it moves down again. And again, we have a different representation up here in layer one. So we can associate that different change pattern again with this location in the behavior model. Then we staple, which makes a click, and we detect a significant event, and it resets the clock. And this reset clock signal makes us move one element further in the sequence. So now we have a new reference frame at that element in the sequence.
Yeah, kind of like the new state.
Yeah, exactly. This is new state of the object. Everything can be at different locations again. And we kind of assume that we stay in the same location within that reference frame. Like it's still the same reference frame. It's just conditioning what features we would expect at the locations can change. And so the stapler opens, time passes, we get the orange representation, and now the flow pattern is moving upwards. We associate that upwards pattern with this location at this time event. Time passes again, we associate this and this with this location in the stapler's reference frame. And yeah, that would be basically it. That's the general idea. And then the learned model for this kind of behavior I just showed would be that there are two states or two intervals. And the one state has like 3 different durations since the last event associated with it. There's at the event, a short duration afterwards, and a longer duration afterwards. Those are kind of the representations in layer 1 that continue to change as time passes. And each of those has a different flow pattern associated with that location in space. Then significant event. We're in a new state. And that one again has two different kind of features associated with it. Both have slightly different durations since the last event. And yeah, during inference, we would basically, in addition to testing different orientations of the object, we would test different states. Like we would start hypotheses of being in a bunch of different states, and then try and match, see which of those match the features we're currently sensing. But we don't have to test the different durations since last event, since those are externally provided by the global clock also during inference. So the global clock also ticks during inference. So during inference, we already get this kind of red, orange, yellow signal. So it tells us like which one we should expect right now. So we just do inference on these discrete intervals or states.
Yeah, that makes sense. And is there a reason the arrows are kind of shown superimposed rather than kind of like at different positions in the reference frame?
Because that's all still at the same location, so the sensor hasn't moved. It's always at the same location in the reference frame. It's just at that location we're observing different changes at different times.
Okay, interesting. So the sensor's staying totally still.
Yeah. Like if the sensor would move down here, then this yellow one would move down here, and we would associate the changes detected there with this location in the reference frame.
Yeah. Yeah, I was just thinking because like sometimes we talked about with like the smooth pursuit and stuff that it would kind of more create a path, but then yeah, I guess
Well,
it's
I
difficult to
tried-
get the input feature to change in that case. And
Yeah, I tried to leave smooth pursuit out of this example because last week we said that we wouldn't kind of start with that, and
Yeah.
it's kind of complicated because the sensor is moving and the feature is static, but we want to interpret it as the feature moving and the sensor not. So yeah, I thought this was the simplest example to illustrate it because it shows how like at the same location you can associate different changes at different times.
yeah, one thought is just whether I'm just trying to see what my eye is doing. I think to a certain degree, maybe if when you're not doing smooth pursuit, what you probably do is kind of a bunch of saccades that are very short and or like so you'd be moving and then but you'd be pausing at each one, so you'd catch a glimpse of movement and then you'd move. I mean, it's not that important. It's obviously not that relevant to the time thing. It's just trying to think through how we represent the behavior reference frame. But yeah.
Yeah, so basically I wouldn't if I implement this now, I wouldn't change anything about how we represent space or the reference frame here. It's still like you add a location in the stateless reference frame and you're associating changes at that location. Now there's just an additional conditioning on what changes you expect there based on the time since the last event and where in the sequence you're at. And then if we were to do like supervised learning, for example, we could move the sensor as much as we want and just tell it like what is currently the element in sequence and time since last event. It would learn it correctly. It's just going to get complicated once you don't tell it that, and for it to consistently kind of infer. Well, it shouldn't be that hard, I guess. It just needs to be able to detect the significant events somehow, or someone needs to detect them.
Yeah, I'm trying to think of what really makes a significant feature. It's the way you describe it here is like a sound of the click or.
So I've been kind of thinking about pendulums, pendulums, and thinking like in that case, a significant event is when it basically goes to the edge and there's a moment where it's still, and then it goes into motion again.
Yeah.
And I guess this is kind of the same kind of deal where not only is there a point where it's sort of at rest, but then it also reverses direction. So maybe it's like the fact that you do have some sort of like expected motion, but then you hit some limit and then you have to reverse direction. Is that something we could use to like qualify something as a significant state?
Yeah, I was thinking about saying that the significant event is just the change of direction. But then I thought it's maybe a more interesting example if the event is detected somewhere else, just to illustrate that this clock is kind of global and can be reset by a bunch of stuff, and the sensor itself doesn't even necessarily need to observe that event.
But yeah, I like the idea of kind of almost like the smoothness of the prediction. So like it doesn't necessarily need to be like reversing direction. But if it's just like suddenly it gets hard, or like suddenly the nature of change is just different, and predicting is, you can't just like predict based on almost like low level first order stuff, then you would kind of chunk it and be like, okay, this is now a different kind of sequence of behavior or something.
I think Rami, you were going
Maybe
to say
did.
something else?
No, I was gonna say, yeah, I noticed the same thing as Scott, that maybe it's the keyframe where, you know, the object is just staying stable, like it's not moving. And I was thinking whether, you know, that keyframe is basically feeding into the behavior. Basically when to
Oh, yeah.
freeze the time.
Like basically the morphology model of the stapler recognizes
Right.
the closed state. Yeah, I think a bunch of things like that could be significant events. I could, for example, if the clock moves much further and we decrease the threshold for significant events, I could imagine events like the orientation aligns somehow, like in a straight or 90-degree orientation, as significant events. Kind of like if you see an object just smoothly spinning like this, you might just artificially set events when it's like upright or sideways. And like that yeah, it could be really minor things that define these events at some point. It would just be important that it's kind of consistent events that you see every time you see that behavior, and that can then reset the clock.
I also like what Neil said about the prediction error being a change, like a boundary, a change in between, like moving to the next element in the sequence. It seems very plausible.
Yeah, and it does seem like, to the other point, like when humans see any kind of repetitive behavior, you do kind of develop, I feel like, kind of a pulsing representation of it, where it's like, it doesn't feel truly continuous. It's not like, if it was truly continuous, then you would just, you wouldn't even really perceive it as repeating. You would almost perceive it as constantly changing. But it's the fact that you kind of notice that it's cycling, and it's sort of the beat
Yeah.
of that cycling that kind of naturally emerges in your head.
Yeah, it's like with the dot that spins on a circle, but you know when it laps, you know when it starts repeating again. Whereas if you look at like a fire or the ocean or something, there isn't really like a point where you say, oh, now it starts over again, unless you watch like one of those YouTube videos that have like smooth jazz in the background. But
Yeah, fire is a good example of like something that doesn't feel cyclical at all.
yeah,
Yeah, I guess like going back to the time cell thing, when I was thinking about the pendula during this last presentation, if we imagined the ball started here at one end, you start the clock, it goes like this. Let's just forget the right side for now. And then, you know, the time cells are clicking down. And then, but eventually when we get back to the beginning, if this thing had learned the association with that early time cell, the state is now saying, oh, I was already associated with the time cell, and it was at the beginning of the sequence.
oh, yeah,
And so now we can restart the sequence, because I've developed an association between what the time cell is and what this morphological state is, and that
Yeah.
time cell was like an early sequence time cell. That's kind of what I was thinking about for like detecting cyclical.
yeah, that's a really great point. Actually, basically, like does this cell down here, this location down here, if it sees a feature at the beginning of the interval, it changes, and then it sees the same feature again. That's the signal that it's back at the
Right.
beginning.
Yeah,
Yeah.
that's your reset, like a cyclical reset signal.
Yeah, I like that. That might be the easiest mechanism, actually.
Does that event signal reset a vote?
No, I don't think voting would play too much into this, because basically since this is a global clock, it's already broadcasting widely everywhere. So I don't think we would need voting anymore for a significant event detection. I mean, we would still do voting on like which object we're sensing, or maybe also where we are in the sequence, but we wouldn't vote about whether the event has reset or not.
So would we see a sequence like A, B, C, D, A, D, or A, B, like a sequence that has a repetition of A, for example, but it's not really cyclic. It doesn't repeat the same thing. The second A should not be bound to the first element in the sequence. It should not know that it needs to repeat. It basically needs to, because the number sequence is A, B, C, D, A, D, not A, B, C, D, A, B, C, D, A, B, C, D. You get what I'm saying? It's
Like a higher
Yeah,
order
so
sequence. Yeah.
I think, yeah, in that case, like basically each letter would be one of the elements in the sequence. And I guess the reset I was thinking of right now was like what triggers moving one forward in the sequence. In your example, like each letter would trigger moving one forward. Whereas, I guess, yeah, I think that's a good point. Like it doesn't solve us knowing when this whole sequence restarts. It just solves like if we only have continuous change within one of those intervals. How do we know when that kind of starts over?
Yeah.
I think the event stuff plays into this quite a lot. Like, if we do have a continuous stream of ABC, ADF, or whatever, so it's a higher order sequence, but there's no like rest period in between that sequence, then it is quite hard to learn that like sort of higher order sequence. But if there was like ABC, ADF, break, ABC, ADF, then that break gives us an indication that that first A is the beginning of an order sequence. It's a significant event. And so that second A, when we come across to it, yeah, maybe we would associate with a, yeah, I feel like it helps somehow. But I'm not
Yeah,
sure.
I mean, even with music, it's like you often like play the first note a bit louder, a bit more of an attack on the first note, or you have like some kind of beat in the background that tells you that what do you call it? The 4/4 rhythm starts over again.
Yeah.
Yeah, and I could kind of imagine like you can almost imagine like a threshold for like kind of like you were saying, you're like maybe that gets lower as the sequence gets longer. But you have kind of some threshold for saying, okay, the sequence is repeated. And yeah, with a kind of challenging sequence like that, like it might almost be a bit of kind of trial and error where you're trying to predict what's happening, and you might not initially know where that repetition happens. Like I don't know, I can almost imagine this if you were like reading like genetic sequence or something. If you were just doing that, and you would see like a bunch, and you probably wouldn't initially reset it at all, but maybe at certain points you'd be like, hang on, is that a reset? And then you'd kind of update your hypothesis about where that reset point is, and then you keep going, and then you'd be like, oh yeah, maybe that is the reset. And you could almost like tune that point to align with how yeah. And
So
or
like
like the
HTM,
pendulum, like when you first see the pendulum swing, you don't really know when it's going to stop and change direction, but then yeah, I don't know.
Yeah.
like HTM solved the higher order sequence thing, right? So like it could correctly deal with like ABC, ADF.
I don't think it does.
It would treat that second A as different than the first A because of the it was
Yeah,
preceded.
it does that part. It doesn't resolve the issue of how do you kind of in an unsupervised way detect the start of a sequence versus the continuation of a longer sequence.
So it seems like we could just augment that logic as it is. And instead of thinking about A's as completely independent identities, there's an SDR for that first A and it's SDR for the second A, and they may be similar. But when we're talking about resetting a clock, the similarity of that, I don't know.
But I think the
Similarity.
different,
It's
I
tough.
think that representing the same feature differently is solved by having the reference frame down here and kind of moving through the sequence here as like, although the same letter A might be coming in, it would be we would be in a different element of the sequence and then predict a different next element in the sequence. But then, yeah, like Neil said, I think it wouldn't solve the like figuring out whether the A was in the middle or if it's restarting again.
Well, for what it's worth, like revisiting the Vivane paper that you brought up last week, there were, when I was in the lab and was involved in studies where we did have sequences like A, B, C, D separated by a gray screen versus just let them run without a gray screen in between. And there were like, it's actually quite hard for the mice to show like the kind of prediction errors that you get when you don't have that gray screen in between. It's possible, but having that sort of reset teaching signal or some clear event indicating the beginning of the event has like a quite a large impact on whether or not like prediction error like signals emerge afterwards.
Interesting. That's great. That fits perfectly with this idea, right?
Let's see if I can find the paper.
Oh, by the way, just one side note. The time cells that Scott showed last week had like finer resolution at shorter time intervals. So that could be easily integrated here by basically putting more neurons here at the beginning and then making them less and less towards the end. And there wouldn't need to be any change in the learning module. Just have like a coarser resolution in the beginning, a finer resolution. And like it would change more frequently here, so it could represent more detailed differences in the changes.
Let me just, I'm going to put this in the chat here. If you go to figure 2, there, it
If
shows
you want to share your screen, I stopped sharing.
So it's this one oddball evoked responses, yada, 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 V1.
Oh, hey, look who the first author is.
Yeah.
That's cool.
So here's one showing the with and without gray, essentially. So you have ABCD, ABCD, ABCD with gray, ABCD with gray. And so, these are the comparison of the responses. You don't have to worry about OSG or RPG, I guess, too much. The different stimulus types. But
Yeah,
essentially,
that's cool.
the kinds of deviations that you were able to get from that 2014, I think it was 2014 Good Morning paper, are, pretty different when you don't have intermediate gray screens to sort of indicate stimulus onset or sequence onset.
I think this matches what Niels has been talking about the prediction error, because now every time you see gray, never mind. It's you're always learning the prediction from D to A or D to gray to A, so it's not about prediction error. But does the gray period change, or is it always the same time period?
Like a second or something like that, I think.
But yeah, you were saying with the gray, it's better prediction, kind of, right? They
Yeah,
kind of understand the sequence better.
Yeah, definitely. Like if you don't have that gray period, you're essentially just doing like Markov chain learning. You're just learning transition probabilities between sequences. And it's just a harder task to do in like an automatic way than if you have something to set the clock at the beginning, which is actually kind of why I was thinking when you were originally going over the clock and there's a new event being set at every single note. Intuitively, it kind of feels like the clock is set at the first note. And then, we tick along and learn the few notes until maybe there is that rest period or something to kind of reset the entire event clock.
Right. And I kind of wonder on that, what could be a bit of both. That like, because it feels like both are kind of useful, and yeah, whether you'd almost have like, in the same way that we have different spaces for objects, that we have like different time starts. But this is really interesting because basically the issue with the top is like the animal needs to infer that D is the end of the sequence. It has kind of very little signal for that. And so blue, just to interpret it, blue is high firing rate because of a high prediction error in the continuous case, or
Talking about here?
yeah, or I'm just trying to see of the traces what's compared with what, or like what should I be looking at?
Different days. So there's a 5-day learning regime. So we're actually not looking at prediction errors here. We're actually looking at the amount of like adaptation over days in this particular case. So when we're saying in the continuous case, it says here green is day 1, blue is day 5, right? So it's saying that there isn't that much of a difference across days when you don't get a teaching signal on the gray. But when you get a gray signal in between, then like the day 1 responses are kind of small, but they grow quite significantly after multiple days of exposure. And it's thought that like this is the kind of adaptation. I have to kind of dig into this paper because it's been a while. We did so many experiments for this paper. I don't actually remember what made it into the final version. So I have to like review it, but it's thought that, the kind of adaptation, the kind of learning you get from having this gray signal is what helped to drive the prediction error signals that you see in the sort of like 2014 paper. And that they just don't seem to emerge quite as robustly when you don't have that gray signal. When you try to learn 4 days of continuous sequences. So anyhow,
Yeah, that's cool.
Well done. Yeah, that's really fitting.
I have to remember what went into this. Yeah, there's a lot of, I can just put this on the chat or something also, but there's a lot of timing related stuff in this paper as well, if you're interested in kind of thing.
Yeah. Okay. That was everything